and the 4p orbitals, which were the T1u orbitals. And then we have seen that the 6 ligand group orbitals, they again are of initially same energy, and they can be categorized under 3 headings: the A1G orbital, T1U orbital, and EG orbital, just as discussed here. So this is A1G, this is EG, and T1U. So the ligand group orbitals are classified under 3 symmetries: A1G, T1U, and EG. A1G is non-degenerate, EG is doubly degenerate, and T1U is triply degenerate, right? And the metal orbitals is such. So if you compare ligand and metal orbitals, then you find that A1G and A1G symmetry is matching, T1U and T1U symmetry is matching, and EG and EG is matching, but there is no matching of the T2G orbital in the ligand set of orbitals in the initial assumption. So what we may say that when they interact, we know orbitals of same symmetry interact. So the A1G, the S orbital of the metal ion, interacts with the A1G orbital of the LGO, and they form a bonding orbital and an anti-bonding orbital. So this is the anti-bonding orbital, this is the bonding orbital. Similarly, T1U LGO, T1U LGO means these LGOs, these 3 LGOs, they interact with the T1U, that is the metal p orbitals, and they again form 3 degenerate bonding orbitals and 3 degenerate anti-bonding orbitals. The EG orbitals of the metal ion, they interact with the EG orbitals of the ligand, and they form a doubly degenerate bonding orbital and a doubly degenerate anti-bonding orbital. And T2G orbital, since there is no matching orbital in the case of T2G, so what happens that the T2G orbitals remain non-bonding. So we have 3 bonding orbitals, 3 anti-bonding orbitals, these are the anti-bonding orbitals, and we have a non-bonding orbital. And since we know that the energy gap between T2G and EG is called delta O, so here the delta O is this energy, and as you can see, this energy gap is actually difference in energy between the anti-bonding EG orbital and the non-bonding T2G orbital. Remember that each of the ligand brings a pair of electrons. So 6 ligands brings 12 electrons, that means 6 pair of electrons. Now this 6 pair of electrons, obviously here we have 1 pair, here we have 3 pair, and here we have EG pair. So these lower bonding orbitals will be completely filled up, right? Because the 12 electrons will be accommodated, 12 electrons donated by the 6 ligands will be accommodated in these 3 sets of bonding orbitals. A T2G orbital will contain electron depending on how much number of electron in the 3D orbitals are there, and there may be electron in the EG star orbital or not. So this energy gap in terms of molecular orbital theory, so the energy gap between the non-bonding T2G orbital and anti-bonding EG orbital is your the crystal field splitting. Now from this MO diagram is more satisfactory than the ligand field, than the so-called ligand field diagram or crystal field diagram. Why? Because in the crystal field theory, we have hypothetically assumed that the metals and ligands are point charges, and there is only electrostatic interaction, but there is no covalent interaction. But from all the experimental details and theoretical calculations, we know that metals and ligands cannot be treated as point charges, and indeed there is substantial covalent interaction between the metal orbital and ligand orbital. So that reality, both experimental and theoretical inputs, suggest that there is appreciable covalency. I will not go into the details of the experimental evidence in favor of covalency, but there are enormous amount of experimental data which suggests appreciable covalency in the metal ligand bonding that is taken care of by the molecular orbital theory. And another thing I have told you at the beginning of the crystal field theory discussion, that please remember crystal field stabilization constitute around only 10 to 15% of the total bonding energy. Main bonding energy is constituted by the overlap of the s and p orbitals with the ligand orbitals, and that you can see justified in this molecular orbital diagram. So main bonding energy is coming from these 3 bonding orbitals, and out of these 3 bonding orbitals, only these 2 orbitals are Eg orbitals where we have sufficient contribution of the metal ion, but the main bonding orbitals are this T1u and A1g orbitals, which are actually s and p orbitals. So the thing which I have told you previously is justified in this MO diagram, where you see that really the main bonding is constituted by the overlap of the s and p orbitals with that of the various ligand orbitals, and the overlap of the Eg orbitals with the various ligand orbitals also constitute a substantial portion of the bonding energy, around 10 to 15%. But crystal field as such, the crystal field splitting is only a small part of the total bonding, right? Only a very small part of the total bonding. But this particular crystal field splitting plays enormous role in determining the trends in certain bond energy or certain other physical and chemical parameters, all because this part remains constant throughout a series, almost constant throughout a series. And as a result of this part plays very important role in determining the overall trend. Now, as you can easily understand, that the crystal field splitting is then governed by the T2G and Eg star splitting. Now, obviously, greater the destabilization of the Eg star, because T2G is non-bonding, it is not changing in energy. Eg star is anti-bonding. So greater the anti-bonding nature of the Eg star, so Eg star will go more and more up, and so the crystal field splitting increases. So according to the MO theory of chemical bonding of transition metal complexes, we can say crystal field splitting will increase when there is more amount of strong sigma bonding, because strong sigma bonding will lead to strong interaction of the ligand Eg orbital with the metal Eg orbital, and this will cause the bonding orbital to go down and anti-bonding orbital to also go up, and this anti-bonding going up of the anti-bonding Eg orbital will lead to increase of the T2G Eg gap. So we may say that if the ligand is a beta sigma donor, or more the basicity of the ligand, so greater the basicity of the ligand, better will be its sigma donor property, and so the Eg star energy will increase more, and as a result of this, crystal field will increase. So in terms of MO theory, I repeat how the crystal field, at least in this description, how the crystal field increases. Crystal field will increase as the ligand becomes a beta sigma donor, right? Because beta sigma donor means there will be more overlap of the Eg and these Eg orbitals, and so this Eg star will go up, and so the crystal field splitting will increase. Now that means greater the basicity of the ligand, greater will be the crystal field splitting. And this can be easily explained again if we consider iodide, bromide, fluoride, chloride, etc. Fluoride, we know fluoride is the strongest base, and so it has got the highest crystal field. Iodide is the weakest base, and so it has got the very weak crystal field splitting. But this sigma only picture, so this is only sigma only picture. In this MO diagram, we have not considered any pi bonding. But this sigma only picture cannot explain many facts of the spectrochemical series. For instance, if I consider basicity of hydroxyl ion and basicity of water, no doubt hydroxyl ion is a better base, much stronger base than water. But we find that water has got stronger crystal field splitting than hydroxyl ion. So this anomaly of hydroxyl ion and water cannot be explained by this crystal field diagram, right? This diagram I have taken from Atkins books, Atkins-Rivard books. So this cannot be explained by this diagram. Similarly, in terms of basicity, we know that ammonia is a stronger base than pyridine. Ammonia is a much stronger base than pyridine, because pyridine nitrogen is sp2 nitrogen, and this ammonia nitrogen is sp3 nitrogen, and sp2 nitrogen has got more electronegativity, so it is less donor, right? Lesser donor. So, and obviously pyridine again much stronger donor than base than acetonitrile. But what do you find? That pyridine and though ammonia is much stronger base than pyridine, so according to this diagram, ammonia should have got much stronger crystal field than pyridine. But experimentally, we find pyridine and ammonia lying very close to each other, almost identical crystal field splitting, right? Pyridine and ammonia. So this anomaly of pyridine, ammonia, hydroxyl and water cannot be explained by this sigma only picture. And also carbon monoxide as such is a very weak base, very weak sigma donor. So why carbon monoxide is a such a strong crystal field splitter, right? Why carbon monoxide has one of the most strong crystal field splitting, that cannot be explained by this very simplistic MO diagram. And I repeat, this MO diagram, in this MO diagram, we have considered only the sigma bonding part. We have not included any pi bonding part, because we have considered, when we have constructed the ligand group orbitals, we have considered first of all 6 sigma donor orbitals of the ligands, which we have combined to get 6 LGOs. So this MO is constructed from 6 sigma donor ligand orbitals, and as a result of this, here no pi bonding is incorporated. And as a result of this, this very simple MO diagram is unable to explain the anomaly between hydroxyl ion and water, anomaly between pyridine and ammonia, or anomalously high crystal field splitting of carbon monoxide. So this diagram needs some correction, right? Because it cannot explain many things. And in order to get correction for the diagram, what we want to do, we want to introduce the pi bonding into the picture. Now, how pi bonding comes into the picture? Now, this is the metal ion, and here you have 6 ligands, which are called 1, 2, 3, 4, 5, 6. Again, this diagram is taken from some book. I have not given the reference because it is not available easily. What you can see from this, for each of the ligand, you see there are 2 arrows. Right, there are 2 arrows. These arrows means there are 2. So if this is the sigma orbital, so along the axis there is the sigma orbital of the ligand, and apart from this sigma orbital, there are 2 other p orbitals of each of the ligand, which may act as pi orbital. So these 2 arrows indicates perpendicular. This is the sigma along the Cartesian axis. There is the sigma bonding orbital of the ligand, and along 2 other perpendicular directions given by these arrows on each of the ligand corresponds to 2 p orbitals, which are of pi nature, And here I have shown that for each of the metal orbitals, metal T2G orbitals, dxy, dxz, and dyz, how the different p orbitals may interact. For instance, if I consider dxy orbital is in the xy plane. So in the xy plane, what are the ligands? 4, 5, 2, and 3. So you see 2, 3, 4, 5. 2, 3, 4, 5 are the ligands which are there in the xy plane, and for each of them you see this is the dxy orbital, and you see there are, for each of the ligands 2, 3, 4, and 5, there are certain p orbitals which are p pi orbitals, which is suitable for lateral overlap with this dxy orbital. So here we find a matching, here we find a matching of lateral overlap, here we find a matching of the lateral overlap, here we find a matching of the lateral overlap. So dxy orbital can laterally overlap with 4 p-pi orbitals, and so this lateral overlap will lead to pi bonding. Similarly, dxz orbital, again, if you consider dxz, so in the xz plane, what are the ligands? 3, 5, 1, and 6. So you see 3, 5, 1, and 6. These are the ligand, and again you see that corresponding to dxz orbital, we have 4 p orbitals of 4 ligands which can do lateral overlapping, resulting in pi bonding. So the T2G orbitals has got appropriate symmetry where it can overlap laterally with the p-pi orbitals of the ligand, and so it may participate in pi bonding. Now, apart from p orbitals, some ligands like say phosphine, right, or some sulfur ligands, some thiolate ligands, they may have filled d-pi orbitals. So pi bonding may be of 3 types. One is this p-pi d-pi overlap, where p-pi is the donor and this d-pi of the ligand is the acceptor. So the T2G orbitals of the ligands are a metal ion is called that the acceptor orbital. Vacant T2G orbitals are the acceptor orbital, and the filled p orbitals on the ligands, they are called the p-pi orbitals. They are the donor. So p-pi d-pi bonding, where p-pi is donor and d-pi is the acceptor. D-pi orbital is from the metal and p-pi orbitals, filled orbitals, are from the ligand. Now there may be other type of pi bonding where we may have a d orbital of the ligand overlapping with the d orbital of the metal, and here, so it is a d-pi d-pi overlap. Now in d-pi d-pi overlap, generally there may be 2 kinds of thing. One is that the metal is the acceptor and the ligand is the donor. That means this is filled up and this is vacant. Or in many cases, there may be opposite case. That means when we have a metal ion in a low oxidation state or metal ion containing many number of electrons, then this d-pi orbital of the metal may be filled up, and the d-pi orbital on the phosphorus or sulfur may be vacant, as is usual the case in phosphine or thiolate. And so there may be what is called a back bonding, where the metal d-pi orbital is the donor and the ligand d-pi orbital is the acceptor. So here we have a d-pi p-pi bonding. This is simple pi bonding where ligand is donor, metal is acceptor. The other thing may be a d-pi d-pi kind of bonding, pi bonding, where in most of the case the ligand d-pi orbital is vacant, so it is acceptor, and metal d-pi orbital is filled up, so it is donor. So d-pi d-pi back bonding, this is called back bonding. When metal is giving back pi electrons to the ligand, it is called kind of back bonding. So it may be a d-pi d-pi back bonding kind of case. Or a third kind of pi bonding is possible, where a filled d-pi orbital of the metal interacts with the pi star orbital of a ligand like carbon monoxide. This is the carbon monoxide, and for carbon monoxide, this is the anti-bonding pi star orbital, and this anti-bonding pi star orbital has got proper symmetry to overlap with one of the d-pi orbitals of the metal ion. So again, it is a back bonding, but here it is d-pi to pi star, d-pi filled d-pi orbital of the metal and pi star orbital of the ligand. So I again repeat, there may be first of all two kinds of pi bonding. One is ligand is the pi donor and metal is the pi acceptor. So metal is pi acid and ligand is pi base. Anything which gives electron is base and which accepts electron is acid. So in this first case, ligand is pi base and this is pi acid. Acceptor is acid. So metal d-pi orbital is pi acid orbital. So there may be this kind of bonding where ligand pi orbitals are giving back electron or giving electron to the vacant d orbitals of the metal ion. So just as sigma orbital is also giving, pi orbital is also giving, so sigma and pi working in the same direction, ligand is donor and metal is acceptor. So this is the simplest case where ligand is both sigma donor and pi donor, sigma basic and pi basic, and metal is both sigma acidic and pi acidic, because in both sigma and pi mode it is accepting the electron. So that is the simplest case. The other two cases may be that metal is sigma acidic because it is accepting sigma donation from the ligand, but it is pi basic, meaning it has got excess pi electron, and this excess pi electron is given back to the ligand in the form of a d pi bonding or a d pi star bonding. So vacant pi star orbital gets electron back from the metal, or vacant d pi orbital gets electron back from the metal. So these are called back bonding. And again, this back bonding concept you have some introduction in the school, I mean 11-12 classes. So if I consider now both sigma bonding and back bonding, so I have cut down this other part because this part is unaltered. E.g., this part remains same whether there is whether there is pi bonding or not. So apart from this, the only thing that will change is this part. So I have concentrated on this part, forget about the other orbitals which are bonding and anti-bonding orbital. So in the absence of ligand pi interaction, here we have, so when you have only sigma bonding from the ligand, here you have a non-bonding T2G orbital and anti-bonding Eg orbital, Eg star orbital, and this energy gap is delta O. Now we consider that the ligand is participating in pi bonding also. Now I have told you there are two cases. One is the first case where ligand is pi donor, right? Ligand is both sigma basic and pi basic. So when ligand is pi donor, so that means ligand contains pi electrons also, T2G electrons. And these T2G orbitals are vacant, fully vacant or partially vacant. So now this T2G orbital of the ligand interacts with the T2G orbital of the metal and causes a bonding orbital and anti-bonding orbital. Now the bonding orbitals are completely filled up by the T2G electrons from the ligand. So this is basically a ligand orbital which is completely filled up. And this is the metal orbital which was initially non-bonding, but now T2G orbital also has acquired some amount of anti-bonding character. Now you see, when ligand is pi donor, what it is doing by virtue of pi donation, it is pushing up the electron of the, it is pushing up the energy of the T2G orbital, because now it has made T2G orbital as the anti-bonding orbital. So the energy gap between T2G and Eg decreases, and as a result of this, crystal field will decrease. So what we proved from here, that whenever this non-bonding T2G orbital, initially non-bonding T2G orbital accepts electron from the pi bonding T2G orbitals of the ligand, this will result in this T2G orbital of the metal ion acquiring some amount of anti-bonding character, and they are destabilized from their original energy position. And as a result of this T2G gap now decreases. So crystal field now becomes lower. So sigma donation as well as pi donation from the ligand will result in decrease of the crystal field strength. That means any ligand which is both sigma donor and pi donor will decrease the crystal field strength. On the other hand, if ligand is pi acceptor, then it means ligand has got vacant T2G orbital, and now your metal contains T2G orbital which has got some amount of electron, and they interact in this way. So you form a bonding orbital and anti-bonding orbital. Now this bonding orbital is more close to the metal. So this bonding orbital is T2G in character, and the antibonding orbital is ligand in character. So now this T2G and EG gap, because this is the original T2G orbital, this is the original T2G orbital of the metal, it has decreased to here. So pi back bonding, when metal ion gives electron back to the ligand by virtue of pi back bonding, that leads to stabilization of the T2G orbital. T2G orbital, initially non-bonding T2G orbital acquires bonding character. So T2G orbital now becomes bonding, and the ligand T2G orbital, by virtue of accepting the electrons, now become antibonding. So now the energy gap between the T2G and EG orbital increases, and as a result of this, crystal field increases. So I repeat this part because this is very important. So this is the sigma only picture. Now if ligand is pi donor also, that will lead to increase of energy of the metal T2G orbital, because metal T2G orbital now acquires antibonding character. So the energy gap between T2G and EG decreases, and hence crystal field decreases. So when a ligand is both sigma donor and pi donor, invariably crystal field will be lower. On the other hand, if the ligand is sigma donor but pi acceptor, that means ligand has got some vacant pi orbital, and this T2G orbitals now has got some electrons to be donated. So that by virtue of this donation, this T2G orbital is stabilized. They are converted to a bonding orbital from a non-bonding orbital. So the energy is decreased, and thus the EG orbital remain unaffected. Thus the energy gap between T2G and EG increases, and as a result of this, crystal field increases. So pi acidic ligands will increase the crystal field strength. Pi basic ligands will decrease the crystal field strength, and that I have written here. Fluoride, which is a sigma donor as well as pi donor, their crystal field is weaker. Carbon monoxide, which is a weak sigma donor but very strong pi acceptor, because of its pi accepting property, the T2G orbital is stabilized much, and as a result of this energy gap is very high, and that's why its crystal field stabilization is very high. That means crystal field splitting is very high. And I have written it here that pi donors ligands like iodide, bromide, chloride, fluoride, they are strong pi donor ligands, and they have got the weakest crystal field. Then very weak pi donor or negligible property is water. So it is more or less intermediate crystal field effect. Ammonia, no pi donor, again it is of intermediate crystal field strength. But when we have a strong pi acceptor ligand, like say triphenyl phosphine or triphenyl artsine or carbon monoxide or cyanide, strong pi accepting ligands lead to high increase of delta O. So pi donor ligands has got very low delta O value. Weak pi donor or no pi effects will have intermediate delta O value, and very strong pi donor pi acceptor ligands will increase the crystal field like this. Now I have told you that I will not discuss the experimental evidence, but as you can see from here, I have given you one evidence here. Here we have taken Hexa Carbonyls, right? Hexa Carbonyls, they are all isoelectronic, except for the fact that as you go down this, you see starting from a plus charge, now this is neutral, this is minus charge, this is 2 minus charge, etc. So these are Hexa Carbonyl and these are tetracarbonyl. Now first of all, you look at the Hexa Carbonyl. All of them are isoelectronic. Now you see, for the Hexa Carbonyl, the IR stretching frequency, this stretching frequency corresponds to the strength. Higher the stretching frequency, higher is the strength of the bond, CO bond, carbon monoxide stretching frequency. So as you go from plus charge to neutral to minus charge, stretching frequency is 2090 centimeter inverse, then 2000, then 1860 centimeter inverse. So down the group, as you go from plus to neutral to minus, the stretching frequency decreases. That means carbon monoxide C triple bond O, that bond strength decreases, and that is because there is more and more, starting from the plus charge, if you go to neutral and negative charge, obviously the electron donation power of plus charge will be less, the neutral will be greater than the plus, and negatively charged metal ion will have greater ability to donate back the pi electron. And greater the donation, as you can see here in the carbon monoxide, electron is going to the pi star orbital. So if pi star orbital is located, obviously pi bonding will cancel out, and as a result of this, bond order will decrease and the stretching frequency will decrease. So as we go from MnCO6 plus to CrCO6 to VOCO6 minus, you see down the group the stretching frequency decreases, and this is because the pi back bonding capability of the metal ion increases as the positive charge on the metal ion decreases and negative charge increases, and greater the pi back bonding, smaller is the pi bonding of the carbon monoxide, and so the stretching frequency decreases. Similarly, if you look at this system, this this is 2 minus, so 2 minus again further decreases. Then if you go to tetracarbonyls, again you find the very similar thing, right? So NiCO4 2060, then minus charge 1890, 2 minus charge 1790. So both with the hexacarbonyl and tetracarbonyl, you find that as the negative charge on the metal ion increases, the pi back donation ability of the metal ion increases, and as a result of this, the carbon monoxide bond strength decreases, and that is reflected in the stretching frequency. I will not go into the tetrahedral thing, MO theory, but what I want to explain here is the anomaly. First of all, here, suppose, so if there is between ammonia and pyridine, I have told you ammonia has got stronger, ammonia is stronger base than pyridine. So if ammonia is stronger base than pyridine, what we expect, without taking into pi donation, what will happen, that the T2G non-bonding has got identical energy, but since ammonia is a stronger donor, so E star orbital will be more destabilized in case of ammonia than in case of pyridine. So in the sigma only picture, we expect in the sigma only picture, in the sigma only picture, stronger crystal field than pyridine. This is if we do not consider any pi bonding effect. But I have told you experimentally it is found ammonia and pyridine are almost identical. Why? Because so for ammonia, this is the picture, there is no pi bonding, so this is the T2GG gap. Now for pyridine, initially this is the gap for sigma only picture. However, pyridine has got vacant pi star orbital which can undergo back donation from the metal ion. So for pyridine we have vacant T2G orbital like here, and this T2G orbital, vacant T2G orbital, vacant pi star orbital of the pyridine can interact, can undergo back bonding from the filled T2G orbital of the metal ion. So there is interaction, and so T2G orbital energy of the metal decreases, T2G orbital energy of the ligand increases. So now you will find that the T2, once you take into account both sigma donation and pi donation into account, then you find that the T2G G star gap of pyridine and ammonia, both of them are almost identical. So ammonia T2G G star gap is fully responsible by, is fully split up by the sigma only picture of the ammonia. But for pyridine we have sigma donation as well as pi accepting. Sigma only donation will give you lower crystal field than ammonia. But once you take into account the pi accepting property of the pyridine, then this pi accepting property leads to lowering of the T2G orbital, and as a result of this, the overall T2G gap is almost identical for pyridine and ammonia, and that's why they are of very similar crystal field strength. This figure is very well given in Kiter books. So, and very often question comes in the exam about this pyridine ammonia anomaly or the water hydroxyl ion anomaly. So you should consult any book and you can get it that. So here also I have considered water and hydroxyl ion. So again, here what happens, suppose this is the T2GG gap for water, and this is the T2GG star gap for hydroxyl ion without taking into account the pi bonding. So hydroxyl ion, because it is a much better sigma donor than water, so in the sigma only picture, the T2GG gap for hydroxyl ion is much larger than the T2GG gap for the water. So we should expect in the sigma only picture that hydroxyl ion is a much stronger base, and so it should have got a stronger crystal field splitting than the water. But unlike water, which is very poor pi donor, hydroxyl ion is a very good pi donor because it has got vacant p pi orbital on the OH and because of its negative charge. So here you have the field T2G orbital of the hydroxyl ion. It interacts with the vacant T2G orbital on the metal ion, and so it destabilizes the T2G orbital. It becomes T2G orbital of the metal becomes antibonding orbital. And now you can see that after taking into account the pi interaction between the p pi orbital of the hydroxyl ion and the metal T2G orbital, now you can see that T2G star gap between of the hydroxyl ion is in fact smaller than that of the water. So whereas in the sigma only picture we should have hydroxyl ion having higher crystal field than water, but when we consider both sigma and pi bonding into account, what do you find? That by virtue of pi donation from the hydroxyl ion, T2G orbital is destabilized, and this causes T2GG gap to be smaller. And so in effect, taking into account both sigma and pi bonding into picture, we find that the T2GG gap of the hydroxyl ion is smaller than that of water. And as a result of this, we find in the crystal field, we find that in fact hydroxyl ion is located at a lower position in the spectrochemical series than water. So these are some of the applications of the MO theory which you must learn from any of the standard book. I shall recommend mainly two books, either the Cyber-Atkins book of inorganic chemistry or the Kiter books, and there these things are discussed, particularly in the Kiter books. The ammonia pyridine case is very, or hydrox, this case is discussed. Please learn, please go through them, because this kind of question comes very often in the exam. So I will stop here. I wish I could have taken one more class to discuss some spectra, but I can ignore that, and I shall also ignore the MO theory for the tetrahedral complexes. So if you learn MO theory for the octahedral complexes, that will be sufficient for you. So I'll stop it here. If you have any question, you can ask now, or you can ask for a tutorial class, and we can discuss your difficulties. Thank you, and wish you best of luck for the exam.
Sir, till this, it is the exam part.
Pardon?
Sir, till this you taught us this is up to exam, right?
This is exam. This part of is the exam. Yes.
Okay, sir. And sir, the assignment you gave us, the class assignment, are we supposed to do in the white sheet or in the lab sheet, like we doing in the lab assignment?
For the theory class, I have given some assignment that you can submit in the way that you are submitting for other classes. But for the lab class, I have given assignment, so I'll tell you that you use some lab sheets, right? These loose sheets are available for lab notebooks, so use that, and use that for For the white part, you draw the diagrams and tables, etc., and equations, etc. And in the line part of the pages, you write the details of the experiments. I mean, the theory and results and all these things, right? You whatever you want to write, you write in the line pages, and in the white pages, you write you can draw diagram, you can draw. You can draw the tables, right, and etc.
Okay, sir.
Okay. And if you have any difficulty, you can arrange a tutorial class where we can discuss your difficulties before the exam. Okay. Anything else? So I think officially your class is supposed to be ending by 1st April, right?
Yes, sir.
So I think because I will not get any more class, so I will stop it here. And so wish you best of luck for the exam. And I repeat that if you have any difficulty, your class representative can, or some of you can arrange a tutorial class. We can discuss your difficulty. Thank you. Okay, and in Wednesday, as Juma ma'am has told you, that there will be a lab quiz, right, where we shall give you say a set of questions from the inorganic, organic, and physical practical part, and we shall set sometimes say 1 hour or something like that, and within that 1 hour period, you have to write down those quiz questions and submit it in the classroom, and that will be done during the lab period that is allotted, that is from 2:30 to 4:30. That in the time schedule, we shall arrange a lab quiz where a joint question from organic, inorganic, physical will be posted in the classroom which I have created, and there you'll be asked to submit your assignment within 1 hour. Is it clear to all of you?
Sir, the questions will be from experiments.
Obviously, question will be from experiments. Of theory of experiments will also be there, because I have discussed the theory. So there may be certain equations, right? Say redox equations, like say reaction between cupric ion and iodide ion, or the reaction between dichromate and ferric, or I may ask you to balance the dichromate redox reaction using ion electron method. This kind of this kind of thing. Okay. Clear? So you must practice those things. That means at least for inorganic part, suppose dichromate redox reaction. What is the how many electrons are being consumed? How you can balance a dichromate half cell reaction using say ion electron method or something like that. Okay, that you must practice. And whatever theory I have discussed of the iodometric reactions, the precautions, the why we are adding phosphoric acid, that kind of thing. What is the role of phosphoric acid, etc., right? What is the advantage and disadvantage of using dichromate and permanganate? What is primary standard? What is secondary standard? Right? These very elementary questions that you must study for the at least inorganic part of the quiz. Okay.
Sir, how many questions in quiz?
That we have not still yet settled. So I have to sit with the organic and physical teachers. So maybe see, it will be around say 10 marks for each, right? So that I can say how many questions doesn't matter, but probably it will be 10 marks for each organic, inorganic, and physical, right? So maybe 2 to 3 questions for inorganic, organic, and physical each. Small questions, definitely small questions, right?
Okay, sir. Okay, sir.
Okay, thank you. Any other query?
Hello, sir. Please, can you please keep a extra class regarding the questions, like can you please discuss what kind of question will be asked in the
No,
exam?
I cannot
Like,
discuss what type of question that you have to search in the previous exams. What I can say that if you have some questions and some doubts, I can take class to clear your doubts.
okay, sir.
Okay. Oh, I can have that, because but I cannot actually I am not very inclined to discuss questions, etc. Right, because I have avoided it. Okay? Because you can go through say 3 or 4 years questions and you can easily understand what kind of questions will come. And please also, what I want to tell you, that you see this is a joint kind of class. So group, along with group 5, certain other sections are also having the same chemistry class, right? So what I will advise, that you will also consult the other sections, because it is a joint question. So whatever has been taught in other sections, that you must also keep track of, because that will help you ultimately in the exam, right? Because it is not that group 5 will have one set of questions and the other groups will have another set of questions, not that. So since it is a joint question, obviously we have to consider whatever part has been taught in other sections also, so it will be like that. Okay. Any other query? Okay, so let us leap, and if you have any more questions after the even you can after the practical, after the submission, if you want, you can discuss more about the nature of the question itself. Okay.
Okay, sir. Thank you, sir.
Thank you. Okay. Thank you to all.
Thank you, sir.
Oh, I'm leaving. Okay. Thank you.
Thank you, sir.